Let's now talk about calculating the critical point of our phase diagrams. And so, to find the binodal and the spinodal, we looked at curves of our delta G mixing. And in particular for the spinodal, we found that the range that it covers corresponds to the portion of the curve that is concave down. And that's bookmarked by, or bookended by, this XA dagger and XA double dagger. Right? So, the curve I'm showing here is just for some sort of arbitrary temperature below the critical point temperature. But in general, as you get closer and closer to that critical point temperature, your A and B points here, they're going to get closer and closer to one another until eventually they're going to be equal to the same value. And so the temperature at which XA dagger and XA double dagger are equal to one another, that's what we call the critical point. So critical point is temperature in which XA dagger is equal to XA double dagger. Right? All right, and so that condition occurs not at the first derivative or second derivative, but instead it occurs at your third derivative. When that's equal to 0. Okay? And so in order to find the critical point, what we need to do is we need to take the third derivative of the delta G mixing. And to show you an example of this, let's once again return to the regular solution theory. So for the regular solution theory, we have the third derivative of our delta G mixing. Once again, I'll divide it by kBt. So we have the third derivative of XA ln of XA plus 1 minus XA ln of 1 minus XA plus XA 1 minus XA chi AB. Alright, and so if we go out and take that third derivative, we get the following. Squared plus 2 chi AB. That's going to be equal to 0. Alright, and so for the critical point, it's going to be satisfied by this equation 3 here. Of course, in this equation we actually have two unknowns. We don't know what our critical point composition is, right? And we actually also we haven't really defined, or we haven't actually solved for the chi AB as well. Okay? Alright, but it turns out that in order to get these two values, right, these two unknowns, we need one other equation. And so that other equation that we're going to need is the second derivative that we used earlier. Right? Because when we were calculating the spinodal, we said that where the second derivative is equal to 0, that corresponds to the spinodal. And for this critical point, we're actually still looking at the spinodal. It's just at the part of the spinodal in which these two compositions are equal to one another. Okay? And so we actually need to solve those two spinodal equation at the same time. So I'm just going to rewrite it here. And so if you solve those two equations simultaneously, what you get is that your XAC for the regular solution theory is exactly equal to 1/2, and your chi AB is equal to 2. Now if we take a look at the full phase diagram, here's the critical point value. If we draw this line all the way down, we find that for the regular solution theory, that composition is exactly 0.5. Okay. The chi AB part, that's going to be useful because that is how we're going to get the critical temperature, Tc. So to get Tc, we need to relate it to our interaction parameter. Okay. All right, and if you remember before from the definition of the interaction parameter, we define the following. So that the interaction parameter obeyed this equation and so to get Tc, we just rearrange this equation and solve for T, essentially. So Tc is equal to this epsilon b divided by 2. Okay. And here we could actually plug in our chi AB value. Or put a comma C here. So we find that Tc is equal to 1/2 Z over Kb. So we just plugged in the 2 for that. And we get this value. Okay? So for the regular solution theory, this is what our critical temperature is going to be equal to. If we go back and review the phase diagram, in this case, for our chi AB, we kind of just said it followed this sort of temperature relationship. And so once again, this 5,000 represents this stuff. Okay. Anyways, for that sort of definition for chi AB, we could go through our critical point analysis and then calculate the temperature, and it corresponds to about 300 Kelvin in this case. Okay. And so, once by using that delta G mixing equation, we're able to calculate the binodal, the spinodal, and our critical point composition and temperature.